Welcome to lecture 22, which is on remote sensing sensors and platforms. So, in the last lecture we discussed for example the broad classification of the sensor, but in this lecture we will discuss specifically some of the satellites and their sensors and the characteristics which we can use for various applications. So, we begin with this lecture here. We have several types of the sensors, as we have seen in our earlier lecture also. The sensors vary depending upon our purpose for which they could be used, and these sensors which we are using in remote sensing could be categorized into different categories. It could be a panchromatic camera which provides us only the black and white image. Then we can have a multispectral scanner, we get more than one band data, so that we can use the spectral characteristics of the wavelength region in order to capture those images, and we can create color composite also from the multispectral images. Then we have thematic mapper data where more than 4 band data is available. Now we have infrared band also. Then we have these thermal sensors. If we want to study the temperature characteristics of the data, then the thermal sensors are very useful. Hyperspectral sensors are providing us very large number of images within a short narrow range of the spectrum. Then we have the microwave radiometers working in the microwave region, because the microwave region has special characteristics as compared to the visible part of the spectrum. And then we have the synthetic aperture radar data where we can get actually the distance also characteristics from the data. Now, sensors can be categorized on the basis of the platforms which we are using. So, what are those platforms? As we can see that we have ground based platform. So, we have for example terrestrial laser scanner which we are keeping it on the ground, we are close to the object. It could be airborne, keeping in the aircraft, we are talking about the aerial photogrammetry or the photographs which are taken by the drone system or UAV system, or the spaceborne, the satellite sensors. So, depending upon the platform these sensors are there, depending upon the geometry and altitude. So, geosynchronous and sun synchronous satellites are there. So, operating from the different altitude, providing us the data at different resolution and a different coverage. Then which portion of the electromagnetic spectrum is used, that is also important, and the sensors have been designed to operate in those parts of the spectrum. We have the sensors, optical sensors which will work in the visible part of the spectrum, then the infrared part, thermal part and the microwave part. So, some sensors are providing us the data in some part of the other, so that we can use it for specific analysis and application part. Then it could be on the basis of the instrument used, whether we are using imaging instruments, we are using some altimeter or a spectrometer or radiometer to collect the digital data about that particular feature, or we are collecting the reflectance value of that feature. Now, further we can categorize them into low resolution or high resolution. You know, today we have a term called very high resolution. So, very high resolution versus very low resolution, where the resolution could be 30 centimeter, 40 centimeter to more than 1 kilometer, and that is the kind of a range which is available to us. In terms of the spectral resolution, we call it the hyperspectral sensors and mono and multispectral sensor. So, when we have very large number of spectral band, the selection of a particular wavelength or particular band is also very important to us. Then categorization could be made in terms of its radiometric resolution, very high resolution to very low resolution. So, whether we have 6-bit data or we have 12-bit data, you know, 12-bit data is always better than the 6-bit data. So, on the basis of that also the categorization of the sensor has been done, and also lastly on the basis of their specific application, whether we are working on the weather or environment or urban mapping or water mapping. So, depending upon the application part also, the sensors have been categorized, because there are certain sensors which have been launched for specifically for ocean monitoring. There are sensors which have been launched for pollution monitoring, for environmental monitoring. There are sensors which are specifically used for cartographic work, so that you can prepare topographical maps of the area. So, we can see there is a range of satellites and range of sensor. This list is not complete, this is just an example. We have a Landsat satellite, spot satellite, ASTER, IRS images, spot images, AWIPS images from IRS, MODIS data, AVHR data, GOES data. So, these all that data sets are shown in this particular slide. So, what is important to visualize from the different data sets which are available to us in multispectral mode, that the amount of information or the kind of maps or kind of thematic data which we can extract from these images, they are different in nature. So, they are at different scales, different area coverage, at different level of informations are available from these images. Now, major if we talk about the polar satellites and their sensors, very popular these old satellites which are continuing into series also, the Landsat, OSPOT and IRS. So, we will discuss in this lecture the some characteristics of these satellites where the data have been used worldwide for large number of application. So, when we are talking of the American satellite, the first satellite which is called Landsat satellite, this was launched in 1972. Prior to that also the satellites have been launched, but they were not so successful and available, the data was not available to the public. So, 1972 the first remote sensing satellite was launched by NASA and later on handed over to the NOAA. This satellite was called ERTS, which is Earth Resource Technological Satellites. So, ERTS was launched. You can see how the satellite looks like from the pictures here. Before the launch, the bottom picture is before the launch and the top picture is after the launch. It was quite heavy, 2200 kg, the length was 4.5 meter, width was 3 meter width, because it carried the solar panels also. You can see the 4 solar panels on one side, similarly on the other side also there. And since 1984, the operation of the satellites and data handling is managed by a commercial company which is called EOSat. Okay. So, EO stands for the Earth Observation, the satellite company. So, this is the starting and beginning of the remote sensing satellite from 1972 onwards. So, this satellite is a sun synchronous satellite. So, it was actually 8° off the polar orbit. So, it was making the 8° angle. The orbit was completed in 99 minutes, one orbit. So, per day 14.5 orbits were completed by Landsat. Repeat cycle was 16 days. It means that every 16 days the whole earth will be covered, and 17th day will get the image of the same area as we got on the first day. It completes 233 orbits for each 16-day cycle. So, you can see in the left diagram also the orbit paths are shown. It will cross the equator around 10 am, and most of the satellites between 10 am, 10:30 am. So, this is the average time when the sun angle is low and you get very bright images because of the less pollution also. The swath width is 185 kilometer wide. So, its width on the ground covered by one movement of the satellite 180 kilometer wide strip on the ground. So, if we take across also 185 kilometers, so one scene One Landsat scene was covering 185 kilometer by 185 kilometer on the ground. So, it is a huge area, very large area one could see from one particular Landsat scene. If we see a little history now of it, it is a series of the satellites. So, after Landsat 1, Landsat 2 was launched in 1975. So, if you remember that I told that 5 year is the design life. So, we have to launch next satellite prior to 5 years. So, that the continuity of the data is maintained. So, Landsat 2 was launched in 1975, although the Landsat 1 continued till 1978, 6 years of life. Then afterwards, subsequently Landsat 3, Landsat 4, Landsat 5 in different years. Like in 1978 Landsat 3 was launched, in 1982 after the 4 years of that Landsat 4 was launched, and in after 2 years 1984 5 was launched. So, these satellites were launched with some improvement. So, on the basis of the feedback, on the basis of the limitations which we found in the earlier system, then some improvement was done, and the subsequent satellites which were launched, they had that improvement. So, Landsat then 6 was launched October 1993, but this satellite failed. So, it could not reach the desired orbit, the desired height, and it failed, it collapsed. Then Landsat 7 was launched in 1999. So, after 84, the next satellite which became operational was in 1999. Until that, those satellites, earlier satellites, kept on giving us the data for the whole world. So, the advantage of these satellites was that anywhere in the world you can acquire this data, you can procure this data, you can place the order with this data and use this data for your study. Then Landsat 8 was launched in 2013, and Landsat 9 was launched very recently in 2021. So, you can see it is a long list of the series of the satellites which have been launched, with the modification over the previous one as far as the quality of the data, as far as the resolution of the data is concerned, spectral wavelength is concerned. So, that changes were made, and many times you will find that these satellites were giving the data in parallel, overlap was there. So, the next satellite is launched, the previous one is working. So, you can see in this particular diagram, which is a Landsat timeline starting from Landsat 1, which is in 1972, and the horizontal bars are giving us actually the overlap which we received from the various satellite. The overlap was there. So, during that overlap region we can get the repetitivity of the data, that is in a temporal data was available to us at a reduced interval from these satellites. When we have the overlap, we can use the data from one satellite, and then after some time we will get the data from the second satellite, and the temporal resolution you can reduce, repetitivity of the data. You can get very quick data from the Landsat itself. So, about the sensor systems which carried by these 1 to 8 satellites which I have mentioned, various kind of sensors were there which have been designed and operated. The RBV was in Landsat 1, 2 and 3, they had the return beam Vidicon camera systems. So, like a video camera take the images in 3 spectral wavelength region. Then the MSS is a multi spectral scanner, will provide the data in 4 spectral wavelength region, and then thematic mapper data was operating in more than 7 spectral wavelength region, data was provided to us. And then we have enhanced thematic mapper. Enhanced thematic mapper means that there is some improvement over the thematic mapper, and that enhanced word was added to it. Then afterwards even some more improvement was done. So, the improved version was called ETM plus. So, the ETM plus indicate that this is the improved version of the sensor system over ETM. Then in Landsat A, for example, we had OLI, operational land imager systems are there. So, I am not going into very much detail of these sensor systems, but as a whole, what are the different sensors which have been used by this Landsat series, and what is the quality of the data, what is the speciality of the data. For example, RBV sensor, if we are talking of return beam Vidicon cameras, the first 3 satellites, 1, 2 and 3 satellites, they employed RBV camera, and then MSS camera was started, and then it provide us 80-meter resolution with 4 spectral bands. RBV was also providing us 79-meter resolution. So, 80-meter resolution means the pixel size is 80 meter. So, that we assume that any object smaller than that dimension may be difficult to identify from such images. So, we could get this data in visible green and near infrared wavelength region. Visible part of the spectrum, we used to get 4 images of the same area. So, when we have the 4 images, we can actually carry out the analysis of these images together in order to identify the optimum number of features which can be identified from these images. Then MSS multispectral scanner, and then later on thematic mapper came, which was employed in Landsat 4 and 5, 2 types of sensor. So, RBV was dropped, and then we had MSS and thematic mapper. So, we are getting 4 wave images from MSS, 7 images from thematic mapper, but at different resolution from both the sensors, but 11 images of the same area. So, we have good wealth of information about that particular area, because this is captured in different parts of the electromagnetic spectrum. So, this was using the whisk broom technology, across track scanning. When it is moving, it is doing the across track scanning. The satellite MSS has a oscillating mirror, which was actually creating some kind of error in the data set, also distortion in the data set. So, this MSS technology was later on dropped. So, it had a poor radiometric resolution also. The MSS was operating in the 6-bit data. So, 6-bit is 2 to the power 6, 64 values, DN values were there. So, how that RBV looks like, this shows that this is the arrangement, the 3 cameras, then 2 cameras were fitted, and these 3 cameras were looking at the same area. Then these 2 cameras, they were looking at the adjoining area. So, we had 3 cameras which were providing the 3 images of the same area in different wavelength region, and the swath width was 185 kilometer. So, it was the scene size was also 185 kilometer by 185 kilometer, but later on it becomes 183 kilometer to 163 kilometer, and these 2 RBV cameras were looking at the adjacent area, successive scenes. Landsat MSS and RBV. So, this is the figure diagram of Landsat satellite, and you can see the RBV systems where these camera systems are fitted at the bottom part of that. So, this is a RBV system where the MSS system, this is the RBV 3 camera systems which are fitted over there. So, these sensors are carried by the satellite, and then they capture the incoming radiations. If we look at the spectral wavelength region, in which spectral wavelength region this MSS multispectral scanner was working, it was working in the green part of the spectrum, red part, near infrared part of the spectrum, and the wavelength range was 0.5 to 0.6, 0.6 to 0.7, 0.7 to 0.8 and 0.8 to 1.1 micrometer. So, about 80 meter resolution. So, we are getting the data. So, here it was an oscillating mirror, and because of that oscillating mirror, our scanning of the surface was done as it is shown in the diagram. The line is inclined because by the time the scan starts from one end to the another end, the satellite has moved some distance from north to south. So, when the satellite is also moving, there is a scanning part and there is a rotation of the earth. So, we are getting actually this type of scanning. The scan lines were not horizontal, but it was slightly inclined, and because of that we find that the format of the satellite image was little skewed kind of it was not exactly square format or a rectangular format. Landsat TM, because it has more number of bands increased, and resolution also we have 256 DN value. So, it was 8-bit data instead of the 64 grey number value. So, green band, red band and infrared bands were making it better to discriminate the vegetation cover from highly sensitive to plant vigor. So, here we are showing you two images here. This is taken August 14, 1999, another was is taken October after some time. So, these are the two images, and we can see that there is a difference in the color also, and this color is due to the growing season of the crops in the area. So, one can find out particularly this particular region. If you see here, you find that there is a difference in the color, and it is because of the crops. In one season it is growing, in another season it is not there, and because of that we can get the difference. So, once we are using the images of different season and different year, we can find out the kind of crops which is available at one particular instant and changes in the area which is taking place. Landsat TM data, thematic mapper data, it was giving us 7 spectral bands, and the advantage over the multispectral band was thermal infrared band, inclusion of the thermal infrared band, and this thermal infrared band was operating in a thermal region. So, 10.40 to 12.50 micrometer wavelength region, and its resolution was a little poor than the remaining images. But these thermal infrared images were very helpful when we are talking of the geological mapping, geological structures we have to identify, or we have to correlate the object with their thermal temperature. So, these images were found to be even at 120 meter resolutions were very helpful in order to carry out the small scale mapping of an area. So, if you see the configuration of Landsat TM, this is the place where the thematic mapper. So, this is the place where we had the multispectral MSS, RBV was dropped. So, there is nothing like RBV here. Then we have a global positioning system antenna which will give us the coordinates of the point also. So, we have a multispectral scanner and the thematic mapper sensor which will provide us the continuous data in 4 band plus 7 bands 11 spectral wavelength region. Then in Landsat 4 and 5, which are called the next generation satellites, because some modification was done over Landsat 1, 2 and 3. So, these had thematic mapper in it, and we know the wavelength region, and this wavelength region we can actually correlate with the color also: blue, green, red, near infrared, thermal infrared, mid infrared. So, we had a very good resolution. In Landsat MSS we had 80 meter resolution, here we have 30 meter resolution data. So, this is the configuration of the satellite, and then the top the TM data which is available to us at 30 meter resolution. So, if you look at the Landsat TM data now, all that mountainous area you can see very clearly the vegetation cover, vegetation growth, and you can see those river portion, the water area. There are some waterlogged areas or the areas where the water is stagnant. So, one can identify such features very easily from this data, Landsat TM data. But if I show you the water features here, dark blue color is there for the water body, and you can see the green color is here for the vegetation cover. So, you can very clearly identify the urban area which are the pinkish area here. So, Water body, in the water body also, if you have the darker color of the water and then you have the lighter color, so it indicate the shallowness of the water and also the forest cover and the urban area, that all can be identified with the help of these satellite images. So, after the TM data, which was Landsat 5 and Landsat 4 had the TM data, then the next was the ETM plus or ETM data 1993 and 1999 when Landsat 7 was launched. This was the enhanced thematic mapper data in it. So, enhanced thematic mapper data was used and the Google Earth mosaic was created with the help of that data. So, this is the ETM plus sensor and you can see the location of that ETM plus sensor, and this is the enhanced version of the thematic mapper. So, here we have some modification in the wavelength region, the repeat period and swath width of this was same as thematic mapper. So, there was no change as far as the repeat period is concerned and the swath width of the data is concerned. So, these are some of the you know characteristics of the Landsat 7 ETM data. So, where we had very large number of bands, 8 bands are there. We have thermal infrared band as we had in the thematic mapper data, but here addition was this band, which is a panchromatic data. So, panchromatic is black and white. So, again the range of this particular data is 0.52 to 0.9 micrometer wavelength region, and the resolution becomes just double of the previous one. So, it was 30 meter earlier, it gives me 15 meter panchromatic data. So, any object which is 15 meter size on the ground, I may be able to identify with the help of this data. So, you can see here that the improvement over the previous one was the addition of the panchromatic data at 15 meter resolution. So, very good amount of detail, amount of information can be identified with this data. So, here I am showing you ETM bands, a combination of the 3 bands in a particular area. This is a true color composite, and the other one combination is showing the false color composites. So, first one is a combination of 3, 2 and 1 band, and the second one is a combination of band 4, band 3 and band 2. So, this is a true color first one. On the right side is the false color image, and in the false color image one can see the forest area pinkish color and the red color, and water body in a deep water and the shallow water in a different color. So, you can see light blue color, you can see very dark blue color, and then one can see the urbanization also very clearly. You can see even the boundary walls which are having very linear kind of a impression. So, one can see the roads, one can see the other surrounding features as well, the tributaries of the river. So, we can identify with this kind of image, we can identify or we can prepare the thematic map, very good thematic map from this data. Then Landsat 8 was launched, and that had a characteristics of the sensor was called OLI, operational land imager, and it was operating in actually 9 bands, that was the advantage. So, we are getting the data in 9 spectral region. So, in addition to band 8, it has band 9 cirrus, and which was operating is 1.360 to 1.390 meter, again at 30 meter resolution. So, what was the advantage of these bands? The advantage of these bands were that a particular wavelength region is more useful to vegetation, the another is more useful to soil, the third one is more useful for vegetation cover, fourth is more useful for the coastal area. So, things like that. So, each band, each specific band has a utility to it. So, this 9 images were obtained from the OLI sensor. So, I will show you the image here and the different bands. So, if you see this particular table which summarizes the type of sensors and the type of data which we are getting from the various Landsat series. So, the first column shows the different Landsat series which are launched with some modifications. So that is why these are categorized Landsat 1 to 3, 4 to 5 in one category, 7 in another, because the ETM plus was done and the 8 was having the operational land imager and thermal infrared sensor was also there. Well, as far as the spectral bands are concerned, you will find that the earlier one were more or less giving us the data in visible part of the spectrum, that later on the infrared part of the spectrum and thermal part and infrared, thermal infrared part was introduced, because we can discriminate the vegetation cover from the other feature, from the soil or from the water features, and then we can further categorize the vegetation cover with the help of this data. Then these thermal bands were also used for geological mapping, identification of the geological structures, the faults and the folds also in the region, and also each object can be correlated with the temperature. There are some objects which are cooler in nature, there are some objects which are warmer in nature. So depending upon the temperature characteristics also we can find out, like lot of climatic change kind of a study has been done, that what is the temperature increase using the thermal data. Spatial resolution, it varies from 80 meter, so it was 80 meter pixel size to down to 15 meter pixel size we have come. Temporal resolution was actually from 18 days we got the 16 days temporal resolution. So every 17th day now we will get the data from these satellite. So these are the different ranges of the data products which is available to us from the various satellites. Now temporal data from the same sensor, from the same satellite. So Landsat image from the same sensor, but taken in 1970, taken in 1980 and taken in 1990, every 10 years, after 10 years. What are the changes which have taken place in the area? If we like to carry out that change analysis, such images are very useful, and it can tell us whether the water body is shrinking or expanding. And particularly if we look at this particular water feature here, this was not in 1970, and now we can see that it has appeared in 1980. And similarly we can find out some changes which are taking place in the other areas. So very change analysis, what are the new features which have come up, whether the forest area has reduced or the water body has water area has reduced, or the new urban area has come up. So that kind of analysis can be carried out with them. This is satellite image which actually has been used for deforestation from 1975 to 2000. So this is 1975 image and this is 2000 image. And 1975 we can see this particular area has a very dense green forest area. That is why the pink and reddish color is shown. But if you look at the entire region now here, that all is deforestation has taken place and it is all urban area. So it has been converted into urbanization, and there is no forest now available in this particular region. So this deforestation could be now related to the temperature changes, what are the climatic changes, what are the temperature changes which has taken place due to this urbanization. So we can hardly see now any forest area in this particular region. So we can identify the different features from the temporal images which are available to us and try to get the product. Now this Landsat data products, they are available to us in the public domain also. That means the free of cost. You cannot get the latest data, but you can get all the old data. So if the data is older than 2 years, then this data is made available at the public domain and distributed by the EROS Center of USGS, and the link is given here, URL is given. So lot of research community, students community, teaching community, they are making use of this free data for research purpose, for education purpose. So this particular data is available to us for the previous years, and we can If we want the recent data, probably we will have to buy, procure this data, but if our application is good enough to use the old data and we can derive some useful results, then this particular data is available free of cost. Particularly from the training point of view, from the carrying out the practical exercise, this data I found is very useful. So, one can download the data and carry out the research work. So, this is all about the Landsat data product. Thank you very much.